Hi there, welcome to Unit 2, Lesson 2, Part 2. And if you watched the previous video, you can probably tell I look like I'm wearing the same thing. We are just knocking them all out. This is what you do when you get a day off, is you just record a whole bunch of lessons. So this part is going to focus on the standard form of quadratics. In the last lesson, we introduced the three main forms. There was a vertex form, factored form, and standard form. And this lesson is going to focus on standard form. We're also going to really dive much deeper into domain and range as they apply to quadratics. So I know that's always a fan favorite for everyone to do domain and range. So let's start off with just the intro to standard form. What is standard form? Standard form is this. This should be in your notes from the last class, but if it is not, make sure that you go and get it now. You can almost be 100% sure that there will be some kind of question on this. So standard form is ax squared plus bx plus c, where A, B, and C, and I'm going to throw some kind of crazy notation out there, are elements of the real numbers. So whenever somebody does this, you definitely want to ask a question. So that symbol right there, I didn't draw it as well as I could have. It should look more like that. It looks like a C with a line in it. That symbol is from a branch of math called set theory, and it means is an element of or is a member of. And then this symbol looks like the letter R, except it's got two lines on the back of it. And that is the mathematical symbol for the real numbers. Okay. Now, you see this right here. Okay. What you right now need to get out of that is just this. A, B, and C are numbers. Okay, that's all that means. That's a super mathy way of saying that they are numbers. So if you tell me that A is equal to 3x, I have to take off points because A does not equal 3x. A is just a number. It is only a number. You only ever tell me that that A is equal to some number, and the same with B and the same with C. So students who say ax squared and 3x squared plus 4x, B is 4x. No. Okay, they're just numbers. Now, from standard form, we want to be able to locate key information. Typically the y-intercept, although we're not going to focus on that today. We also want to be able to find the vertex from that form. Now you might be thinking, well, on the last lesson, you said that we would use vertex form to find the vertex. Well, this is true. Vertex form is really easy to get the vertex. Standard form is not as easy to get the vertex, but that also doesn't mean that we won't ever need to find it. Okay, and so we want to be able to get the vertex from this form. We are also, like I mentioned before, we're going to focus today's lesson on domain and range. So we're going to dive deep into the domain and range of quadratics. So to get the vertex, there is a formula. So I'm going to give you a formula, and we're going to talk about the formula, and we're going to give you an example of using the formula, which I'm not sure at this point how I'm going to revise the tests for Unit 2 and stuff. I haven't thought that far ahead. But I know last year there was a problem on the at-home test that required the use of the vertex formula. And so we're going to look at it two different ways, but at some point you are accountable for knowing how to use this formula. So the formula looks like this. Remember, the vertex is an ordered pair, okay? It's x, y. So the vertex is an actual location on the coordinate plane. It is a point. The formula is this. It's the opposite of b over 2a, and that is literally your x value. So if you want to find the x value, you use negative b over 2a, although you might have noticed that I said this instead of saying negative or minus when I said it out loud the first time, and I will continue to do this. I said the opposite of b, and that was something that my geometry teacher got me doing back when I took geometry, when I was memorizing the quadratic formula. He would always say the opposite of b, the opposite of b, the opposite of b, instead of negative b or minus b, which are also correct ways of saying it. But the opposite of b gives a little bit more of a verbal prompt for what you need to do with that. Now, to get the y coordinate, you do this. You do f of the opposite of b over 2a. And most students are going to look at that and get a little bit of freaked out because there's a lot of parentheses happening there. And it's also using function notation, which we're not really comfortable with at this point. But here's how it works. To get the x value, you're going to take the a and the b out of the formula like that we just had on the previous slide, and you're going to throw them in here, and you're going to get a number for x, okay, just some kind of number. And then what you're going to do is find f of whatever that number is. So like, let's say you throw everything in here and you get like 5. Then to get the y coordinate is going to be f of 5. In other words, it is the y coordinate when the x coordinate is 5. So here's how the formula works. You plug a and b into the formula, and that's going to give you x. And then you plug x into the original function, and that's going to give you y. And then you have x and you have y and you have your vertex. So that's what the formula looks like. Typically, you will see this on reference sheets and such, but knowing like how to use it is often another whole thing. All right, so that you should copy down. So you definitely should have the vertex formula written down. And if you need to, copy down that little summary, because if you're looking at your notes later, you want to remember what you're supposed to do with that formula. So plug a and b into the formula to get x, then plug x into the function to get y. So here's a quick example. Okay, we're only going to go through this once. So we've got y equals 2x squared plus 8x plus 12. And so we'll start off just by identifying like our a value, our b value, and our c value. Okay, now we don't need the c value for this particular kind of question, but we'll just point out that that's what it is. Now, notice that I did not say that a is 2x squared. A is not 2x squared. A is just a number. So a is 2. If you do not see a number out front, the implied number is 1, meaning you only have 1x squared, and so your a value would be 1. So the way we would start this is we would write down our formula. X is equal to the opposite of b over 2a. And then notice where this verbiage comes in handy. The opposite of b. B is 8. What is the opposite of 8? That's right, negative 8. Not usually an issue with positive numbers, but it is with negative numbers. Over 2 times a, well, a is 2. And so we have our order of operations. Negative 8 is just there. 2 times 2 is 4, and 8 divided by 4 is negative 2. So when I'm looking for the vertex, the x coordinate of the vertex is negative 2. To find the y value, we are just going to take the negative 2 and plug it in everywhere there is an x. And what I strongly encourage you to do is to use Desmos for the calculation here. Just to review order of operations, though, again, I expect you to use calculator for this. We would start with parentheses. If you look at your parentheses here, there's literally nothing you can do in those parentheses. So you just have like negative 2 and a negative 2. So good luck with that. After parentheses comes exponents. So we need to do the negative 2 squared. I will point out it is only the negative 2 that is being squared, not the 2 out here. So it's negative 2 times negative 2, which is going to give us a positive 4. If you want to, at this time, you could do that multiplication with the 8 and the negative 2. I just opted not to. After exponents comes multiplication. So 2 times 4 is 8. 8 times negative 2 is negative 16. and then we have the plus 12. And then with adding and subtracting, we always go left to right. And the reason we go left to right is because really that subtraction there, that 8 minus 16, if we wanted to, we could write it as 8 plus negative 16, and now it's all adding, so we would just go all left to right anyway. So adding and subtracting always goes left to right. 8 minus 16 is negative 8. And negative 8 plus 12 is positive 4. And so my y coordinate is positive 4. So that is some work. It's not an overwhelming amount of work. I hope that nobody is absolutely panicking at the amount of work there is to find the vertex there, but that's how it works. So you use that formula, the opposite of b over 2a, that gets you your x value, and then you plug the x value into your formula, and that will give you your y value. And then together, you have the vertex. So let's talk about this a little bit more in depth. What's the problem with this procedure? Now, this isn't necessarily an issue with the procedure itself, but rather you as a student being able to carry it out. So I want you to take a moment to think from a practical standpoint. What issues might you have with this long term? And it's not that the procedure is super hard. So nobody says the procedure is super hard, like I'll never be able to do it. But just think from a practical standpoint for you. You're staring at your test, you're asked to find the vertex using the formula. What's going to be the problem? All right, now I paused for a little bit there to give you time to think. Usually that's about all it takes in my classes. Somebody in the class will blurt out, I'll forget it. It's not that the formula is super difficult. Nothing that we showed on that slide was it was order of operations and arithmetic. The problem is that students forget it. That formula kind of came out of nowhere. I did not justify for you where the opposite of b over 2a came from. Now that is something I can show you that actually does come from a procedure that we carry out on the formulas, on the different equations, but I didn't show it to you. So if you don't know where that formula comes from, there's a decent chance you're going to forget it. So you could memorize it, you could copy it down for your homework, memorize it short term, but long term, the real issue is I just don't remember this formula. So what other method would also work and likely make more sense? Like, how else could you probably find that vertex and you're not going to forget how to do it? All right, I paused to give you time to think, and usually someone in the class will blurt out, I could find that vertex using Desmos. If I could plug that equation into a graphing utility, I would just have to look at the graph and I would be able to find the vertex. So let's just go through that. Now, right now, you guys, I don't think are going to see this, but I'm going to see it. Right now, I'm looking at a view on my computer screen where I can see like the next slide and stuff, and the slide I'm writing on is really small. The moment I click on Open Graphing Calculator, it's going to completely change what my screen looks like, and also creates issues where I can, if I don't have the right tools activated exactly right, I will accidentally click off slides. It has been known to happen. Hopefully it won't. I'm just giving you a little bit of a heads up. So I need to turn off the pen. Okay, so we're going to open the graphing calculator up. And there it is. And I'm going to go ahead and type in and there it is. And because Desmos tries to read your mind, it will give you the vertex, and you click on it, and lo and behold, the vertex is negative 2, 4. Now, when it comes to being assessed on this, there is value in doing the hand calculation. The hand calculation builds an intuition about how these numbers work together and can help when the computer is not quite doing what you expect it to do, and it can help you identify mistakes. So while for testing purposes, you can use a computer to do it. Just remember, if the directions are asking you specifically to use the vertex formula, then you need to go through the process using the vertex formula. So if you are watching this from home to either review or make up and you didn't write down that example does not exist in your notes, please rewind the video and go back and write down the example for how we found the -2 and the 4. Don't just rely on using the computer and the graph to do it. Use the computer and graph to check that work. Again, it's not a super long process. So use the computer to check your work instead. All right, so now we're going to talk about everyone's favorite topics. That's a little bit facetious. It's usually not everyone's favorite topics. We're going to talk about domain and range, and we are going to try to dive a little bit deeper into this. Now, before we even get started, I just want to be honest. Domain and range take a while to get comfortable with. That is not license for you to fast forward through this, saying Miss Taylor does not expect me to be comfortable with it. I don't need to know it. That was her just saying I don't need to know it. You do need to know it. You need to know domain and range. You need to be able to state them and find them. I say that in advance because I don't want you to get frustrated and then quit. Okay. Give yourself the time to get comfortable with it. So listen to the presentation, follow along with the examples, and on your homework, you give me the absolute best domain and range that you can for those problems. In a perfect world, everybody's going to get all of them right all of the time. If you don't, though, that's okay. We're going to keep revisiting this, okay, throughout the year, and it will get better. So give yourself that time to learn in that space to be able to learn. So we have mentioned this before. The domain is all possible X values. Okay. And that should already be in your notes, but if you are forgetting it, you're like, I don't remember. I know she said that in like the last unit somewhere. Write it down again, just all possible X values. That's what domain is. That's a very basic definition. It's not a very mathematical definition, but so there are two ways that we can represent and visualize this. And in this lesson, what I tried to do was I tried to approach this two different ways, using the equation for those of you that are more comfortable with the equation, and then using the graph. For range, the graph is almost universally the easier way to do it. For the equation, it can go either way depending on the kind of function that we're looking at. So with a quadratic, well, with any of them, here's your key question. What am I allowed to plug in for my X value? What am I allowed? What kinds of numbers can I put into this equation and get numbers out? And the flip side of that is there anything I'm not allowed to plug in? Is there anything that's going to cause this to error? It's going to make my calculator error. It's going to cause something to come out undefined. Okay, that's the kind of thing we want to ask. If you're looking at the graph, the key question you would ask are there any I think I want to put in here, are there any points on the graph where the graph does not exist? That feels like a lot for me to have put in that blank, but so are there any points on the graph where the graph does not exist? Okay, and by points, I should probably clarify X coordinates. Are there any X coordinates on the graph where the graph does not exist? Okay, so if you need to copy those down, go ahead. We're going to work through an example on the next slide. If I can find... So we're going to work through an example here with y equals x squared plus 2. So finding the domain of this graph. So on the left, you can see where we have the equation reasoning. And when I said like the equation reasoning, like what am I allowed to plug in? So we want to ask ourselves, can I plug positive numbers in? Like, can I actually go, I'm losing my little dot. Let's change over the laser pointer. Are there any like positive numbers that I couldn't plug in? So can I plug in positive numbers? Can I take a positive number, square it, and add 2? Yes, I can plug in positive numbers. Can I plug in negative numbers? Can I take a negative number, square that number, and then add 2? Yes. Can I plug in 0? Can I take 0 and square it and then add 2? Now, before you say no, throw it in your calculator, okay? Throw it in your calculator. 0 squared means 0 times 0, which is indeed 0. 0 plus 2 is 2. So you can. Could I plug in decimals and fractions? Like, could I take 1/2? Can I take 1/2, square it, and then add 2? Yep. I mean, I don't want to, but that's not the question that's being asked. It's like, could I? Could I take 0.1 or 1.3 and plug it in and square it and then add 2? And so the answer to all of those was yes. There wasn't an issue with any of those. So yes, 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 and yes. So the conclusion is that all numbers are possible. Now, all real numbers are possible. And I want to say that. And so at this point, usually a lot of students will say, what do you mean like a real number as opposed to what? Like a fake number, a made up number? Real numbers would be opposed to what are called imaginary numbers. And we will cover that in a couple months. So don't sweat that. So essentially what we've shown is that any number that you can think of, we could plug that in. And so when we see the D there is for domain, okay? We would express that is like this. We would say D and we would make that funny looking R. Okay, it's an R with like a double back on it. Other ways that you could say it are this. You could say the words all real numbers. Okay, I would accept that. Or you could do this. You could do parentheses and then you could do negative infinity to positive infinity. And that is using a different kind of notation. It's called interval notation, and photomath will often dump stuff out in interval notation, so don't copy it if you don't understand it. But what that means essentially is anything all the way from negative infinity up to positive infinity. So from as far as you could go to the left on the x-axis to as far as you could go on the right. I prefer to use the symbol for all real numbers, but I would accept either of those other two notations. To reason this out from the graph, we're looking for any x coordinates where the graph stops or breaks. And so as you're tracing along, do you see any stops or breaks in the graph? And the answer to that is no. Now, the window cuts off, but what we do know is that this graph keeps going, and it keeps going up, and it also is going to continue going to the left. And so while I can't see it, I could come all the way out here to x is -10, and I could find the graph up there somewhere. Okay, it's going to go completely off my screen, but it is up there somewhere. And I could do the same thing, even though I can't see the graph like over here at x is 5. I could keep going up, and somewhere like maybe like right around in there where my laser pointer is, that's where the graph exists. I could also go out to 10, and I would have to go higher. And you could go out to 100, you could go out to 1,000, and we clearly don't have a coordinate plane that big, but the graph in theory exists there. So what that means is that all of the numbers are on the graph. Like all of the x coordinates are on the graph. That means all real numbers. So you can go any number heading to the left, whether it's -0, a decimal, a fraction. You can go any number to the right, like decimals, fractions. You can plug in 0. If you plug 0 in, 0 squared, you get the 2 there. And so that is how you would reason it from the graph. Now for the range, this is a kind of a text heavy slide here, so be particular about what you write down. The range is all possible y coordinates. All right, now if you prefer to think of this from the viewpoint of the equation, which I don't recommend, it's going to be tough. Like the range is tough to do, but now not with the example that I'm giving you now, because I want to be able to demonstrate that it does work. But yeah, is there anything we cannot get out for the y value? Is there any kind of value that no matter what you put in for x, you could not ever get this number out for y? If you prefer to think of this from the viewpoint of the graph, you would ask yourself, are there any y coordinates where the graph doesn't exist? Okay, so we're like switching from looking at the x coordinates to looking at the y coordinates. So I would write down that in your notes. I'm going to yap a little bit about this blurb at the bottom. Ideally, you should be able to reason through the question from both perspectives, since equations and graphs are two representations of the same relationship. However, you will likely find one resonates with you more, and this is totally okay. So some of you are going to prefer to reason things out using the equation. Some of you are going to prefer to look at the graph. They're two representations of the same thing. And for me personally, a lot of times I prefer doing the domain with the equation, and I prefer doing the range with the graph. And so you're not committing to these. It's just putting some options on the table for how you can reason through it. So here's our example. This is the reasoning for the range going through the equation. So what is the smallest value that x squared can have? And this is why this is difficult to do with the equation, because on your own, it might be difficult to know what question to ask. So what's the smallest value that x squared can have? Well, if I plug in a positive number and I square it, I'm going to get a positive number out. If I plug in a negative number and I square it, I also get a positive number out. Now there's one number that is neither positive nor negative, and that is 0. And if I plug in a 0, I get 0 out. So if you're thinking about what's the smallest value that x squared can have, well, it's 0. X squared cannot be negative, because when you multiply something by itself, it can't be negative. It can only be positive or possibly 0. So the smallest value that x squared can have is 0. So given that, what's the smallest y value that you could have? Well, you would plug in the smallest x squared value, which is 0. We've got to add 2 to it. So the smallest y value we could have is 2. So what does that mean for our range? There are 2 ways you can write it. Most of you will be most comfortable writing it this way. Y is greater than or equal to 2, because that's the notation you've seen before. So y is greater than or equal to 2. Can't be any less than 2. The other way you might write it is this. You would use a bracket to indicate that the values start at 2 and they include the number 2. And they would continue upward to infinity, and you would use parentheses around the infinity, because infinity is not a number that can be included. So if you're using that notation, that means that the value you see there is included, and that means it is not included. Okay, and we will get more into that notation. later. As you remember from the other slide, when we did the infinity and the negative infinity, there was parentheses on both. And that's because those are not numbers. Infinity is not a number. It's a concept or an idea, but you can't include the number infinity on something. But you can include the two. So the bracket would mean that it's included, and the parenthesis would mean that it's not included. There we go. All right, so how would you do this using the graph? For some reason, I put the graph up there. I have a feeling that is a relic. I did edit this PowerPoint, but I didn't take that out. I think it's from a malfunction. I think we had a malfunction with the Desmos working. But for this, look at the y-axis. So I'm going to turn on the highlighter, okay? And we're just looking at the y-axis because we're looking for the range. And then what we would do as we kind of trace along our parabola is we're looking for the smallest y value there is. And there it is right there. The smallest y value there is at 2. And then the y values go up from there. There is nothing on that parabola when you move down into this space. So these are the y values where the graph does not exist. So the smallest value that the parabola can have is a 2, and it goes upward from there. And so you would write that the exact same way. You would say y is greater than or equal to 2, or you would say it starts at the 2 and then goes upward from there. So that's how you would get it using the graph. For me, again, I prefer finding the domain from the equation, and I prefer finding the range from the graph. It just, to me, that's what works. So summary of what we've learned about domain and range of quadratics. Here's the deal with every single quadratic. The domain of every single quadratic is all real numbers. And so you want to write that down. But think about any kind of quadratic that you would ever see. There are no breaks in the graph. Like the graph continues going to the left forever, and it continues going to the right forever with no breaks in it. If you think about the equation, when you see like y equals ax squared plus bx plus c, you can pick any number you want for the x. There's nothing that's off limits. So we will look at equations where there are some things that you can't plug in. Those are called restrictions on the domain. But the domain of every single parabola is all real numbers. Now, when it comes to the range, every single parabola has a minimum and max or maximum value. If the parabola is pointing upward, then your range would be y is greater than or equal to whatever the minimum is. Or you would say it starts at that minimum value and would continue to infinity. If the parabola is flipped, then you're turning it around and y is less than or equal to the maximum value. And in this case, you would say that parabola starts all the way down at negative infinity and goes up to the maximum. Okay, I am not in Algebra 2 going to hold you to one form of notation or the other. And we are going to come back. We're going to talk in a lot more detail about that notation. But that's pretty much your summary. So if you didn't write a whole lot down through that example, and that's fine, this you would want to write down. No matter how many years I teach this and I tell people, the domain of a quadratic is all real numbers. So when you see that on the test and it asks you the domain to be all real numbers, please get that correct, because it is the same answer every single time. And every single year, there are plenty of students who just leave the entire thing blank. And I don't know what to make of that. Doesn't look like we studied if we're leaving it blank, but it's all real numbers, like all the time. It's the answer for every quadratic. Not every function, but every quadratic. So here's an example of one, and let me turn off the highlighter so I can activate the calculator. These should not take a massive amount of time to do. Now, I would maybe honestly, this is just me, I would maybe do a couple problems using that vertex formula just to make sure that we've got it down accurately. But for time, no, you don't really need to do it. So let's go enter this in. Plus x squared minus 4. So there is my parabola. There's my vertex. Okay, so the first part of this done real fast. So I'm going to go turn my pen back on. And so my vertex is at 3, 5. The axis of symmetry is the vertical line going straight down the middle. It must be written as an equation. X is equal to 3, because that is the equation for the vertical line. The minimum or maximum value, we have done this before. This will be y is equal to 5. So essentially the coordinates of the vertex, one of them gives you the axis of symmetry, one of them gives you the min-max value. Now, this last part, this is the new stuff. The domain of every single parabola, all of them, is all real numbers. The range, now here's where you can play for partial credit. Range is y's. Start by writing down a y. That gives me some knowledge. Like I know some of what you know. So the range like starts with the y. We also know that the range is going to hinge on whatever that min or max value is. So we know that the number in play is a 5. Now, if you do not know greater than and less than symbols, you have a 50-50 shot of getting the rest of it right. But just for reference, that is less than. That is greater than. It is the same symbol. The only thing different is which direction it's pointing. And since we read from left to right, then we read it as less than when it's pointing towards the smaller number. We read the symbol as greater than when it's pointing to the large, or when it's opening to the greater number, and that came out wrong. It has to do with the direction that we're reading it in. So if you're reading it this way, it means the smaller number is on the left, and so you would say less than. If you're reading it from left to right and it's pointing this way, remember the alligator eats the bigger number, so it means this is the bigger quantity, so you would say is greater than. So if we want to say that y is less than, then we want y to be smaller than the 5. I don't know what I did there. There we go. Okay, I'm like panicking that I'm going to mess something up. So this would be less than or equal to. And it's equal to because it could also be the 5. Okay, it could be the 5. So that should not take you a long amount of time. Most of that information you can get directly off the graph fairly quickly. Okay, so here is one for you to do on your own. Pause the video, open up Desmos, and see what you can do with it. I believe there is a way for me to stop the video recording here, but I don't want to risk clicking to the wrong thing. All right, hopefully you pause the video. Here we go. Vertex is -1, -3. The axis of symmetry is going to run straight through the middle at the x is equal to -1. The minimum or maximum value, which I did not edit it on that slide, sorry about that, is y is equal to -3, and that is a minimum. The domain of every parabola forever is all real numbers. And the range here, we're going to put the y, we're going to put that -3. And this time it is greater than, because the y's get bigger than the -3. The -3 is the minimum one. So we want y to be the bigger. So the alligator is going to eat the bigger one. Y is greater than or equal to -3. Okay. none of that should take a long time. If it's taking you a long time, then we're overthinking it or we're doing something wrong, and I want you to raise your hand. I want you to tell me about it. So here's your homework. So for problems 1 through 5, state the vertex, axis of symmetry, minimum, maximum value, domain, and range for each parabola. I expect you to do this just the way we did that example and practice problem. I expect you to graph it. I would strongly recommend, though, that you pick 1 or 2 of them and use the formula. Okay? So use the formula on 1 or 2, 1 or 2, or 2 for fun. And then use the graph just to double check. And that will let that formula sink home a little bit more. For 6, graph them on Desmos to check for errors and any corrections, which you're probably solving it that way in the first place. And what questions do you have about this lesson? And that includes questions about using Desmos, okay? That includes questions about scaling it, keyboard shortcuts, that sort of thing as well. All right, so that's a wrap on this lesson. And as always, reach out to me if you have questions.